So we're going to tie up any miscellaneous parts from this chapter, and we're going to practice results learnt and be able to apply knowledge to a variety of problems. Here we go. Problem number 1. Draw an Argand diagram for the solutions of z to the 6 equals that number there. Right. Well, we know there's going to be 6 roots because it's z to the 6, hopefully. What we might also know, what we did last time, I won't do it for this question, well, I'll show you. What we've done in the past is that we've said that that's like z to the 6 equals 2 that thing times 1. Now if you do the 6th root of that thing, let's do that on the calculator. So get your little mate ready. As if you put in the numbers correctly, have a go with me. Funny calculator this thing. So 6, 7, 2, 9. It comes out as a nice number, doesn't it? 3. So actually there you can say that z equals, and if you take the 6th root of that, that's 3 times the 6th root of 1. And then you know the 6th root of 1, one of the answers is 1. So it's going to be 3 times 1, which is 3. So you know one of the roots is going to be there at 3. And then they're going to go symmetrically round in a, don't want to give it away, begins with an H. Hexagon. So what's 360 divided by 6? Hopefully we know that one. 60, so you go round angles of 60. Or you could just have done, if you didn't like that idea of all that, you could have just done, well, one of the roots, take the 6th root of that, so you do 6th root of that, like we just done, hopefully. 6 there, and 7, 2, 9 there. That gave us 3. So we know one of the answers is 3. There are 6 solutions following a hexagon. We only need to find out one yet. So can we carry around in 60s? I know there's going to be one there. That's at -3. And the other two, there's 60 degrees, isn't it? There. There. 6 degrees after that. There. There. And then it should be sort of a regular. Oh, it doesn't really good, isn't that one, is it? We'll make that cross over here. Down there. Hopefully yours looks better than mine. Or in a inscribed circle of radius 3. Right. Right, example 2. Drawing roots. So the diagram shows a regular pentagon inscribed in a circle of an Argand diagram. One of the vertices lies on the imaginary axis. The 5 vertices of the pentagon correspond to solutions of the equation of the form z to the n equals w, where w is a complex number. Find the values of n and w. Well, w must be a complex number, else we'll have had our answers starting on the real axis. There's the real, that's the imaginary. So basically we know that one of these roots is this thing. So what we do know is that z well, z to the n equals w. So z equals the nth root of w. And one of those answers is going to be, n lots of those answers will be root 3 over 2i. Now what that means is that if we did this to the power n, we'd get w. So w would equal root 3 over 2 I to the power n. Now looking at this, we'll know n because it's a pentagon. So because it's a pentagon, so we're going to write that. Pentagon implies n equals 5. So W equals, making quite a meal of this, root 2i to the power 5. Work that out with your friend again. And we should get not a particularly nice number. 9 root 3 I over 32. Okay, so find the values of n and w. We've done it. N's 5 because it's a pentagon, and w is that lovely complex number there. Spot on. Right, next question. It's one for you. Oh, excitement. Right, have a go at that one. I shall read it to you because it's got that draft across it when I did it originally. The diagram shows a square with one vertex at 2, 2. The complex number corresponding to the vertices of a square the complex number corresponding to the vertices of the square are solutions of the equation z to the n equals w, where n is an integer and w belongs to the real. Ooh. Right, have a go at that one. I think someone will pause the video now until you are ready with your solution. Here it is. Here comes the solution, so unpause. Yeah, one of the roots was 2 plus 2i. It's 2, 2. So your w ends up as, you won't bother with all that. I think I'm going to cross it out because it's just confusing. How would you do that? Use your calculator. This thing to the power 4, which is minus 64. Okay. Let's move on. Right, a useful result. Oh, remember that, yeah. Roots of, not roots of unity, that was roots of any complex number, wasn't it? So find the solutions to this thing, giving your answer in Cartesian form. Cartesian form means a plus ib, remember. Right, so what we do when we're doing this type of question, we usually write it in polar form first, don't we? So you can do your button which does real to polar or whatever, but we'll do it the manual way. Minus 81 on the axis would be there, wouldn't it, on the real axis? So the argument is measured from the real axis over, so actually you can see measuring all the way around there, that angle there is your theta. So the arg is going to be pi, isn't it? So, and the length of it's going to be 81. So z to the 4 in polar form has a length of 81, get the negative, and it's cos pi plus I sine pi. Now you remember we said, so I'm going to get rid of the z to the thingy in a minute, we'll take the fourth root. So that would be 81 to the power a quarter And here we'll have, now remember we said it's the same however many times you go round, so that's cos of pi plus 2k pi, and because we're going to put to the power a quarter, we can use Demaurer and put it under there, can't we? The same thing. Because we don't like writing that every time, we often, or we could say then k is going to equal 0, 1, 2, 3, stop at n minus 1. And we don't like writing that, so we usually put it in exponential form, don't we? What is 81 to the power of a quarter? I wonder, I have a feeling I know the answer, but you might want to check it. Yep, it is 3. So that's 3 e to the, you have to write all that again, pi plus 2k pi, ooh, k is funny, pi over 4I, where k is 0, 1, 2 and 3. So you stick the k's 0, 1, 2 and 3 in, you could get them in exponential form. So in exponential form there will be 3 e to the pi over 4I. The next one would be 3 e to the 3 pi over 4I. The next one, 3 e to the 5 pi over 4I, and 3 e to the, keep adding 2, aren't they, 7 pi over 4I. If you want to change those into Cartesian, all you have to do is put them in your calculator, type them in. It's a bit of a faff. 3 shift ln. You have to put in there pi by 4 shift pi ABC4. Then put an I, a little thing, then an I on it, which you can get by doing shift 0. Press that, and it turns it into the Cartesian form. So writing those out is a nuisance. So first one comes out at 3, to write small, 3 root 2 over 2I plus 3 root 2 over 2I. That's the first one. Then the second one, if you press that one, I think that one's minus 3 root 2 over 2 plus 3 root 2I over 2. And the next one, put that one in, you're going to get, well, I might have done these in the wrong order. I haven't. You'll get, there you get that one, don't you? Minus 3 root 2 over 2 minus 3 root 2I over 2. And then the last one, I'm in the way, is that one with a minus. And if you think of them going round the diagram, because here are the roots, remember it's going to make a square, isn't it? So the first one's at real amount that way, real amount that way. So you get 1 there, 1 there, 1 there, 1 there. So this one's got both the minuses on. And if you put it in your calculator anyway, you'll get this answer. But I can't write it on because I'm in the way. Maybe I'll shrink me in a minute. 3 root, oh stop it, 3 root 2I over 2, and then it's There's no an eye on there. Who put an eye on there? Is that you? That'll be James telling me, wanting me. Get rubber. Right, so, and then it's minus 3 over 2. I don't know if that will show up. Probably not. Tell you what, I'll do that last one because it's been a disaster. Up here, the last one is 3 root 2 over 2 minus 3 root 2i over 2. So those are the 4 answers. 1, 2, 3 and 4. Right, spot on. We haven't finished though, have we? Hence, write z to the 4 plus 81 as a product of real quadratic factors. Well, okay, so lost my hat. And so I got to write, hence write the thing in a product of 2 real quadratic factors. Well, at the moment we know the roots, so we can say we knew a root was 2, then we would write z minus 2 was a factor, wouldn't we? So we've got all these funny roots, so we need to write z minus these roots are factors. So we can write our z plus 81. So we write fairly small here, it's in red. So our z 4 plus 81 is equal to z minus 3 root 2 over 2 plus 3 root 2i over 2 times z minus 3 root 2 over 2 minus 3 root 2i over 2 times z minus, we're not going to fit these on, 3, oops, no, we'll do another minus and a minus, minus 3 2 plus 3 root 2i over 2, or another bracket, and that would be times one more of those, z minus, where are we up to now? So we have another minus 3 root 2 minus 3 root 2 over 2i. Those different ones. Right, they're quadratic factors. They're linear factors, but we want quadratic factors, so we're going to have to times 2 of them together. So what we'll do is times those as conjugate pairs, and that should help us get rid of things. So if they're conjugate pairs, when we times them together, there should be no midterm. Well, there will be a midterm. Well, we'll see. But the imaginary bits will disappear. So with this one, nice is it? Right, if we times these two together, because these two are the conjugate pairs, we get z times z, which is z squared. We get z times that, and then you'd also get z times, when you do it the other way around, you have z times that again. So what we end up with is minus 3 root 2z. It'd be over 2, but over 2 again, so that's 2 of them, so that's why it's now over 1. And then you get, that's the middle terms, and then you get that times that. So that times its conjugate friend just means that we get that squared plus that squared, don't we? So we'll get in the bracket that squared, which would be 9 times 2 over 4 plus the other thing squared, which is the same thing, so it's 9 times 2 over 4. So that's horrendous, but that's what you get. And similar with these other two here, these two pairs, so conjugate pairs, we'll get z squared again. We get z times this thing, but you have it twice, so it will be z times, but it's minus minus, be careful so that becomes plus. So you end up with plus 3 root 2 z. And then you've got to get the same thing that's going on as before, so it's the conjugate times conjugate pairs. So again you get 9 times 2 over 4 plus 9 times 2 over 4, which then gives us z squared minus 3 root 2 z, and this thing added together gives us, yes, you guessed it, 9, and the other one will be z squared plus 3 root 2 z plus 9. And there we have it. Hence write it as a product of two real quadratic factors. Right, I want to make us look at this example again because it was that much fun. I'm sure you're having the same fun. I want you to show it in a different, slightly different way, because I've seen this in mark schemes in the past and want you to be aware of it. Now it'll say something like find all, it's the same question, we've got some other excitements on the top. Wow. Cos theta equals those things and sine theta equals those things. Who remembers where they came from? They came from that z plus 1 over z and z minus 1 over z things, if you remember, because it z's I'm confused now. Yes, when z is I'll have to write it down. I'll put it on the next another slide if we have it later, but that's where they've come from, if you remember, a couple of lessons ago. And so we've got those two things, and then we've got this again. So but this time we're going to read this question as find all the complex solutions of z to the 4, giving your answer in, cross that out. You're obviously not going to be writing all this. You might want to make a note of it because I've seen it on the mark schemes. Write it in exponential form, expo form. Then hence do the same things we did before. So if we did it in expo form, well, we've done this a bit ago, haven't we? We don't want to go into all of that again. We've just done the question. So we had back a couple of slides ago, we'd done it in exponential form first. We had this, we had this, we had this, and we had this. The only thing we could argue about if things had to be left in principal form, if you remember, these things have to be between minus pi and pi. And obviously these last two are not between minus pi and pi. So you might want to take 2 pi off them to get them in the range. So that would be, take 2 pi off that, well 5/4, take 2. That equals minus 3/4. And that other one, if you were to take 2 pi off it, and it's 4 pi by I. If you remember, you could otherwise just think of those in an Argand diagram and realise that 7/4 is the same as minus 1/4 pi. Anyway, That's that. So that's part A done. Now part B, write it as 2. We'll see what happens here if we've got them in this form. So in this form, I'll write them out. So it looks nicer, but actually it's more complicated in the sense, but it's what I've seen on mark schemes in the past. So I'll write this out. Z minus 3e to the pi by 4i. So all this is equal to that thing here. Z minus 3e to the, going to couple them up, minus 4 pi, that one. And then we've got Z minus 3e to the 3/4 pi I, before, yeah, pi I. And then Z minus 3e to the minus 3 pi by 4i. Right. Multiplying these together in the pairs, we get Z squared minus 3. Now these are Z's, aren't they? So it's going to be that. And then we're going to have that added on, aren't we? So we end up with, trying to do that as a one step, e to the pi by 4i plus e to the minus pi by 4i z. That's just two middle terms added together. And then we get that one times that one, which would be plus 9, and because they're both e's, add the powers, and it's 0, e to the 0. And on this one, very similar, squash it in a bit, z squared, the middle terms this time will be minus, again, 3 in bracket, e to the 3/4 pi I plus e to the minus 3/4 pi I z, and then again plus 9 e to the, and add the powers, 0. E to the power 0 is 1, so that brings the 9 up. Now this bit, if you recall these things here, look, the similarity with that one, you can ignore that one for now, but the similarity here for that one, that is 2 cos, if you just had the top bit, that'd be 2 cos theta, wouldn't it? So what we've got here is in fact 2 cos pi by 4. So there we go. And similar with this one, we'll have 3, and then we'll have 2 lots of cos pi by, oh no, what are you doing? Pi by 4, silly pen possessed. Z plus 9. Okay, now if you were to press on your calculator, what is cos pi by 4? Well, what you'd find out is that it's, in fact, I think, √2/2. So what we end up with is what we had before. And with this one, there's a minus √2/2. So that ends up making that plus √2z, and then plus 9, and then you're back to what we had before. I think that's worth noting somewhere. If you want to pause the video and someone to note it down, just don't fit on your sheet. Maybe you don't want to note it down, but have a go at it, because we're going to do one on the whiteboards now, and I want you to use that method. Basically that method, because I know that I've seen it on mark schemes before. So please have a go at this question coming up. So if we can pause the video here, it says find in exponential form all the complex solutions to z to the 4 equals minus 16, and then hence express that as a product of two real quadratic factors. So if we could pause the video now before the solution pops up, and that would be great. It'll probably take a little while. So have a go. Do it on the big whiteboards if you like, then you've got some space. Okay, so you're probably about to unpause. Here are the answers for you to peruse for a few minutes. Okay. Right, let's move on to the real stinker of a question. This one is weird, but we'll have to follow it. It's not too hard if we follow it, but it's odd. Okay, roots of unity application. Right, remember those things that we've met before. If 1 omega squared, omega to the n minus 1 are the nth roots of unity, then the sum of those roots will be 0. Now we look mainly at cube roots of unity. But this question isn't a cube root of unity. We're going to see what it is in a second, but we've also got that little rule here down the bottom, which is in your formula booklet, that z equals e to the 2k pi I over n for the roots of unity for when k is 0 to n minus 1. So here we've got this example. It says let omega equal e to the 2 pi I over 5. There's the clue, 5. So what we're after here is the what roots of unity? Fifth roots of unity, yes. And then we've got to show that the real part of omega plus the real part of omega squared equals minus a half. And then go on to show that the exact value of cos 2 pi over 5 is, whatever we find it. So basically we're given that over 5 there. So this thing here gives us the clue that we're now looking at the fifth roots of unity. Now remember, the fifth roots of unity is a little diagram of them. Must start at 1. This is a 1 there. And they go around to make pentagons. So it's 360 divided by 5. Which, if you know what that is, I'll shout at once, but 72. Anyway, so plots, they look like that. And if we were to put the labels on, I've just labelled one, haven't I? But we've got some other labels here. This one would be omega. This is omega squared. This is omega cubed. And this is omega to the power 4. Right, so we can see that the real part of omega, say that would be like wherever it is, and this is a lie, a half across and 3/4 up. Well, on omega 4, the real part will still be a half across, but it'd be minus something down anyway. So really, the real part of omega, in fact, equals the real part of omega to the power 4. Similarities here over here. If this was, say, minus 3/4 along and whatever, half an omega, half I up, half I. What was I saying there? Half I up. It's not half I, is it? See, that was, you know what I mean. So it's half along, 3/4 along, half up. Still, it would be 3/4 along, half down. So the real part of omega squared is the real part of omega to the power 3. Is the same amount along. So how does that help us? So we're after the real part of omega plus the real part of omega squared. Well, we know this fact up here, that the sum of the roots is 0. Now that means that the sum of the imaginary bits must be 0 and the sum of the real bits must be 0. So we can interpret that, press on, as a sum of the, well, there's a sum of the parts, all the omegas to be 0, but we can think of that as the sum of the real parts will also be 0. So 1 is the real part of that. So 1 plus the real part of omega, oops, plus the real part of omega squared, plus the real part of omega cubed, plus the real part of omega to the power 4 equals 0. The imaginary bits would be exactly the same. They would equal 0. Now we can replace, because we've just told me, well, I've just told me, that omega to the power 4 is the same as the real part of omega to the power 4 is the same as the real part of omega to the power 1. So we can say that's 1 plus real omega plus real omega squared plus real omega squared again plus real omega. Take the 1 over there, so we'll have 2 lots of real omega plus 2 lots of real omega, oh, I've put an extra bracket in, real omega squared equals -1. And then you can see what's going to happen, can't you now? If you divide everything by 2, we will get the result that we were after, which was the real part of omega plus the real part of omega squared equals -1/2. So, I'm to go, no, there's another part of the question. The other part of the question said, what is the exact value of cos 2 pi over 5? Well, just stick it in the calculator and find out. Bingo, off we go. No, that's not allowed. You have to show it, hence with this bit here that we've got. Now you might recall exponential form can be written as polar form. So omega, which was, we were given in the question, omega is e to the 2 pi I over 5, is that thing. And how much you can squash on your sheet, omega to the 2 will equal e to the, and that was the one that said it was omega to the 2 was, oh, you didn't know, we'd have to put 2 in, wouldn't we? We'd have to put 2 in as a k, so 2 times 2 times 2 is 4, so that's actually 4 pi I over 5. So that would equal cos of 4 pi over 5 plus I sine of 4 pi over 5. Right, we've just done this bit here. So this is, if I can come here, no, won't let me get the pen. Well, that's the highlighter. Let me have a look. So we've got this here. Yeah, highlights. We're going to hence use that to find the real value of cos 4 theta. So, so we've got the, we're back here. Got the real part of that. So the real part of this is the cos, the i's imaginary bit. So what we've got is that cos 2 pi over 5 plus the real part of omega squared, which would be cos 4 pi over 5 equals -1/2. Now that's not going to get me cos 2 pi over 5 in exact form yet. Now there's a helpful hint here. You've done a lot of these, I'm sure, in normal maths, but maybe not had to spot things like this. Cos 2 theta is 2 cos squared a minus 1. Can you see what I'm going to do now? I want it all in terms of cos 2 pi over 5. What we in fact got here as this 4, scribble it here, cos, now 4 is 2 times 2, isn't it? So that could be written as 2 times 2 pi over 5. Yeah? So our A is that thing. That would equal 2 cos, following the A, squared 2 pi over 5 minus 1. So what I'm going to replace that cos 4 pi over 5 with is this bit here. So I've got cos 2 pi over 5 plus, now this bit now, 2 cos squared 2 pi over 5 minus 1 equals minus 1/2. Right, now we've got a quadratic in terms of cos 2 pi over 5. I'll just write it neatly so you can see the quadratic in the form we might want to see it. So we'd have 2 cos squared 2 pi over 5 plus cos 2 pi over 5, and bringing him over here plus half, so it'd be minus half, won't it? Right, so you've got to keep everything exact. So messy. So you have to use the quadratic formula. So cos, if this was an x, you'd say x equals. So here we're going to write cos. You could let it equal a letter, but it's a little palaver. So that thing equals, now quadratic formula, if you remember that, minus b plus or minus square root b squared minus 4ac, b squared minus 4ac over 2a over 2a, bit rough, right? Anyway, so minus b, so that's minus 1, plus and minus square root b squared 1 minus 4ac, minus, we've got a minus there, haven't we? Minus 4ac, 4 times 2 times a half, so it's going to be plus. So 4 times 2 times a half is 4, isn't it? All right. I think I'm right. Over 2a. Over 2a over 2 lots of 2, which is 4. So what have we got there? We've got minus 1 plus minus root 5 over 4. So that's our answers for cos 2 pi over 4. It's plus and minus. What you've actually got here is the exact answer for cos 2 pi over 5, and also the other one is the exact answer for cos, I'm saying it wrong, cos, we've got one answer for cos 2 pi over 5, the other one's the answer for cos 4 pi over 5. So to decide which is which, I just stick it in the calculator and check. But the one it is by just checking on your machine, if you wish. So we can say cos equals, it's the minus 1 plus root 5 over 4. Final answer, you'll be pleased to hear. So that is a weird question, but good fun, good fun. You may see something like it later on. There is an exam question I've seen that's quite similar, so beware. Right, next question. It's a bit easier as this one, so you can relax. A equal quadrilateral has one vertex at the origin and another vertex at 1, 2. Find one possible set of coordinates for the third axis. So we've got 0 here, we've got 1 at 1, 2 here, and we're trying to find a possible other vertex. Now you're given here, there's a thing, I don't know if you can see it on your sheet. Come on. That angle there, we're told, is pi by 3. Pi by 3. So a little bit of a blurb with this. On the Argand diagram, the point 1, 2 corresponds to the complex number 1 plus 2i. You can obtain the third vertex by rotation through 6 degrees, that's pi by 3, anti-clockwise about the origin with no enlargement. This corresponds to the multiplication of a complex number with a modulus of 1 and an argument of pi by 3. So a complex number with a modulus of 1 and an argument of pi by 3. Let's write it in polar form. That's it, isn't it? So that's what we're going to times it by, and what we're going to times by is this 1 plus 2i. So we're going to rotate that, because remember times in by a complex number rotates it around anti-clockwise. If we're divided, we rotate it clockwise. But we're times in, so we're going to rotate it anti-clockwise. We need to change that maybe into a Cartesian form first. This one was just thinking. So this is cos pi by 3 on your calculator turns out to be 1/2, and cos pi by 3 sine is in fact plus root 3 over 2, and then we times those two together. What will we get? Well, we get 1/2. I'm sure you're shouting this with excitement. 1 times that, well, that's root 3 over 2i. Then we've got 2i times that, so that would be just I, wouldn't it? Yeah. And then these two times together just gives me minus root 3. Group real and imaginaries. It's not very nice, is it? So it would be the chord, if we would be, I don't think you can do anything with that. And then we put the imaginary bits together, plus root 3 over 2 plus 1i. And if you want to do it as coordinates, then coords would just be, would you put them all over? Would you put them all over 2? Would you make it look better? You might. Or it might not look any better. And this one, if you want to write them all over 2 again, you get 2 and you get root 3 plus. There we go. Possible coordinate. How could you have got another one? Anybody think? Don't know if anybody's saying it. If you want to shout it out. If you haven't, or if you're saying the same thing as me, you could have rotated it the other way, and we mentioned rotating it the other way, we just divide. So if you divided by this cos pi by 3 plus I sine pi by 3, you'd have got another possible coordinate for a triangle. Anyway, we didn't send it clockwise, we sent it anti-clockwise in the picture, so that makes sense for the picture. Right, time for you to do some work. You can now go and do miscellaneous exercise at the end of this chapter. Or you can have a go at this question here. Oops, there's the miscellaneous practice. There we are. So miscellaneous practice, page 28, and do miscellaneous. Well, it's just mixed practice, not miscellaneous. Mixed practice 2, page 45. So there's quite a few bits of questions.